Right, we'll carry on with this. Let's just recap our two formula. We know pressure equals force divided by area. That's for like solid stuff, and we write it here. Pressure equals height of the liquid times the density of the liquid times the gravity. So P equals H rho, like a weird P, and then G, gravity, and that's normally 10. And this is B equals F over A. Right. Explain how the atoms exert a pressure on the walls in a container. So it's a 3 marker. Right. This particle's moving, it's got kinetic energy. It hits that with a force, and then it bounces off, and then it hits that with a force. And every time they bounce off the wall, they generate a bit of force. And what is pressure? Pressure is force over area. So that's what we need to write down somehow in right. So we need to write down the atoms or molecules or particles collide with the walls of the container. Each time a particle, no, let's stick to atom. Each time an atom hits the wall, it generates or it exerts a force. And pressure is the measure of force on an or over an area, on an area is probably better. So that's how pressure is generated. So look, 1, 2, 3 points. So just learn them as one thing. That's that done. Explain why the pressure of a gas in a container decreases as its temperature decreases. The volume of the container does not change, so it's a 2 marker. So look, with this we know, let's use that. So we know, first of all, as temperature decreases, the, what is that? Kinetic energy decreases. So the atoms travel slower, and when they hit the and when they hit the wall, they generate a smaller force, and they hit the wall, less frequently or less often. That makes sense because look, when it's going quickly, it'll do this bing 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 bong, Right, when it's going slowly, it'll go bing, 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 bong. So it takes much longer. So overall, what's happening is you're getting less force on the area, so you've got a lower pressure. Right, okay. Let's move on. This looks crazy, this does. Trapped atoms, laser beams, coils producing magnetic field. That looks like a boat or a ship's steering wheel. Okay, diagram 2 shows a device called a magneto optical trap. MOT, eh? I thought that was for cars. Maybe not. Physicists use this device to cool gases to extremely low temperatures. The MOT uses laser beams and magnetic fields to trap a small collection of atoms with extremely small kinetic energies. Each trapped atom has a mass, there's your mass, and a mean speed of 73 meters per second. Calculate the temperature of the trapped atoms. The mean kinetic energy of an atom is that. Right, so they've given you the formula here. So they're saying Ke equals 2.1 times 10 to the minus 3 times the temperature. We know Ke also equals a half mv squared. Right, so we know that formula. So they've given us the mass and the velocity or the speed. Mass and speed. So we say a half times 5.0 times 10 to the minus 27. Right, okay, I'll stick with this color. Just times v squared. V is 73 squared. When you put that into the calculator, you get 1.3 times 10 to the minus 23 joules. Right. Now, look. Now that they've given you this here. So what we're going to do is we're going to substitute that back into there, and we just then work out the temperature in Kelvin. So we know 1.3 times 10 to the minus 23 equals 2.1 times 10 to the minus 3 times temperature. And then we rearrange that temperature because this is okay, because this is physics, let's not take a shortcut. Although the mark scheme misses this step out, 0.63 Kelvin. Temperature in Kelvin. Okay, that's it. Right, let's look at this. So what have they told us so far? So we know pressure is force over area, and pressure is height times rho times g. There you go. Right, let's go. The diagram shows a balloon with a mass attached, held at rest just below the surface. Right, so you've got pressure from the water on there. Right, and you've got pressure, atmospheric pressure on the water. Right, the balloon and the mass are released. The graph shows the velocity time graph for the balloon and the mass as they fall through the water. So you've got a force here. Because it's falling through the water, that means that the weight, which is mass times gravity, is bigger than the buoyancy or the upthrust. Okay, so it's a velocity time graph. So if it's a velocity time graph, the gradient is equal to the acceleration. Okay. Right. Use information to determine the velocity of the balloon terminal. Okay. So what you do is you get a ruler. And you draw a straight line across there, the ruler, and you'll measure this and it'll say 8.2 because this is 9. Right, because this is 9, we know each one of these 5 squares is 0.2. Be careful with that. It's, it can trip you up, so it trips us all up. So that was simply just reading it off as 8.2 meters per second. Explain how the balloon reaches terminal velocity. You should use ideas about forces acting on the balloon. So it's a 3 marker, so let's have a look. The first thing is the weight acts down and the drag. We're not worried about buoyancy, I don't think, at this level. Or there's a force acting upwards, and there's a drag because of the liquid, but we're not interested in that at this level. We're just interested in, right, the weight acts down and the drag acts upwards. Right. At the start, so this is the next bullet point or sentence. At the start, the weight is greater than the drag or friction, so the resultant force causes the balloon. Why did I do capital? No, I can't even spell. Just stop 1 second. Yeah, professionals. Sort of. Causes the balloon to accelerate downwards. Accelerate down. The next thing, as the speed increases, the drag on the balloon increases. So remember, all this is just learn it sort of like step by step, right? Eventually the drag equals the drag equals the weight force and terminal velocity is reached. So look at this, just watch this carefully. Yeah, it's a standard answer, this, to be honest with you. So the weight's acting down and the drag's acting up. At the start, because the weight is greater than the drag, the resultant force is downwards, so the balloon accelerates. As the speed increases, the drag increases. Eventually, the drag equals the weight and you've reached terminal velocity. It's not going to go any faster. Right, okay. pressure, height, density, gravity. Okay, we've done this loads of times. So pressure is height times rho, which is density times gravity. Okay, pressure is height times rho. So remember, this is a Greek letter. It's like a funny P. Okay, let's keep going. Calculate the increase in pressure on the balloon when it has reached a depth of 25 meters. So the density for water is that. So the 2 marker. So what we do is pressure, or the pressure difference, equals height times density times gravity. The height they said was 25. The density they've given there, and we're going to stick to gravity as 10. And the answer is 250,000 pascals, or 250 kilopascals, however they want it. Right, so look, these are quite easy marks. This is why physics is, your maths is up to speed and you can substitute and manipulate or change formula, you're alright. Right, at the surface, the pressure is that, and the volume is, calculate the volume of the balloon at a depth of 25. Right. At the surface, no, I've missed a question, haven't I? Right, done this like I normally do. Move that there, so that's that one done. Right, at the surface, atmospheric pressure is that. And right, what was I looking for? Okay, that was that one. I've linked these two, silly person. Right, the total pressure on the balloon is that. So we know the pressure. So let's do it here. The pressure is right. We've got 25, and they've added. What's the pressure on the surface? Oh, I missed something here. Right, there it is. That's what I was looking for. I've got lost in all the detail. Right, okay. They've said that atmospheric pressure is this. So we've already got, so the total pressure is pressure due to the liquid or water plus the pressure in the atmosphere. Right. So we were given 250,000 pascals plus, right, this will be 1 and 5 zeros, 100,000 pascals, so that answer is 350,000 pascals, or does it say standard form? No, they want you to write it like that, so you can write it as 3.5 times 10 to the 5 pascals. Okay, at the surface area, the pressure is 1.05. That's the volume of that. Calculate the volume. Right. Right, this is the other formula that we need to learn now. We need to learn pressure 1, volume 1 is equal to pressure 2, volume 2. What they're saying is, let me try to draw it properly. I've got a cylinder. and there's a piston there. So I've got this here now. So in here, at this moment in time, pressure times volume gives me a number, yeah, a constant. So I'm not changing the temperature. Now what I'm going to do is I'm going to take this, I'm going to push it in. I'm going to push it in, and what's happened is the pressure, so the first pressure and the first volume. Now for the second pressure, now it's got a different pressure here because there's more particles in a smaller volume. Sorry, the same number of particles in the smaller volume. So you've got P1 times V1, and this is constant. And these two constants are the same. So what they say is the pressure 1 times volume 1 equals pressure 2 times volume 2. So the pressure and volume initially is equal to the pressure and volume after. Right, so this is what they're trying to tell us here. So we're trying to say P1 V1 equals P2 V2. So initially the pressure is P1 V1, which is 1.0 times 10 to the 5 times the volume, which is 0.46, is equal to, we're trying to work out the volume. We know the pressure there is 35 or 3 point. Let's stick to that. Not 350,000, but 3.5 times 10 to the 5 times the volume. We don't know that. And we rearrange that. So V2 will equal 1.0 times 10 to the 5 times 0.46, all divided by 3.5 times 10 to the 5 equals 0.1314 meters cubed. How can you round it off? Does it say 1, 2, 2 decimal places maybe? So we could always write the full answer and then just round it off a sensible number. Normally 2 or more significant figures, but in this case 2 decimal places looks good. Right, okay, we'll call it quits there. We'll try this question on the next one.